Welcome to section 3.6, and what this section deals with is what is called the chain rule. Now, many of you have attempted to use a situation where the chain rule was required, but by not knowing the chain rule, things did not succeed very well. Now, what is happening here with chain rule is that we have functions that are being combined together, not co-functions, but functions of functions, or like f of g of x, or something similar to that. And what you really need to understand is that whenever you have that, we need to use the chain rule. And basically what happens here is the following. If we have y equals some function of x, but we're going to call that u, then to find dy with respect to x, in other words, we want to know what is the derivative with respect to x, not with respect to u. U is very easy. Dy du would be 1 in this case. But what we have to do is we have to take u times, or u prime times du of dx. Now, another way to look at this is to look at, okay, we have a big function, we have an outer function, and we have an inner function. And what we're going to do is we're going to take the derivative of the outer function and then take that times the derivative of the inner function. And here at the beginning, it's not so easy to see that, but as we work along with these problems, it will become a little bit more obvious. I will tell you that you may throw out number 15. Number 15 is not a problem that I'm terribly concerned with. So let's begin with example number 1. We have y equals u times u minus 1. And we're told that u is equal to x squared plus x. So there's several ways we could do this. We could put x squared plus x right here, then put x squared plus x, which of course we'd need to tag on the minus 1, and we can multiply this all out and take the derivative of that. But that's not the point of the chain rule. Instead, what we're going to do is we're going to write this in a more user-friendly form in terms of u. So we get u squared minus u. Now, when we try to take the derivative of this, knowing that u, what we really want to know is what is the derivative with respect to x. So the first thing we're going to have to do is to take each one of these, the derivative of u. So the derivative of u squared is 2u. But then we always have to multiply by the derivative of u, and the derivative of u will be with respect to x, minus the derivative of u is 1, so we'll get 1, but then we need to take times the derivative of u with respect to x. So what this becomes is 2, and we are told u is equal to x squared plus x. So now we can actually start plugging in those values. X squared plus x, and then I need to know what is the derivative of u, du. Well, the derivative of u is 2x plus 1. Minus, okay, 1 times the derivative of u. Well, the derivative of u is still 2x plus 1. So let's see what we get here. When we FOIL this out and distribute the 2, I think we get 4x cubed. Let's see. Plus 6x squared. Plus 2x. Plus 2, and then distributing this negative sign here, we get minus 2x minus 1. And combining all like terms, let's see, we get 4x cubed plus 6x squared. Notice that the 2x's cancel each other out, and we're left with plus 1, I think. And so our final answer is 4x cubed plus 6x squared plus 1. Now here it's not easy to see take the derivative of the outside times the derivative of the inside function. But realize back in pre-calculus, you may have been given a problem similar to this. Y equals x plus 3, the quantity squared, and you were asked to decompose this. And so we would have g of x would equal the inside function, and f of x would be the outside function, or in other words, x squared, not x cubed. So the outside function is squared, and the inside function is the x plus 3. This is the same general principle. You need to be able to split it up into the inside function and the outside function and do different things with it. So now let's look at number 2. Y equals the sine of u, but u is equal to the cosine of x. Now it's really quite simple to now see what is the outside function. The outside function is sine. The inside function is cosine. And so what we have to do is we have to find the derivative of y, what we're going to do is we're going to take the derivative of the outside. Well, the outside is sine of this. So we need to take the derivative of that, which would be the cosine of that, times the derivative of this. Well, the derivative of cosine of x is negative sine of x. And so now we just need to simplify this a little bit further. And unfortunately, cosine of the cosine of x is not cosine squared. We would need to have an x here. So basically, it's just a matter of rewriting this into a little bit more acceptable form, but not really. We get negative sine of x times the cosine of x. Not very pleasing as a final answer, but that's all there is. Keep that in mind. It might be best to plug in the values at the beginning so that you see sine is the outside function, cosine of x is the inside, and it's a whole lot easier to see it from that form. Example number 3. Let's see what we've got here. Number 3, we are told y equals the cosine to the 6th power of x, and it says write the function in the form y equals f of u and u equals g of x. I don't like that. Basically, I want to look at what's the inside function, what's the outside function. Well, right now it may be very confusing as to which one's which, but we have to understand this means the cosine of x raised to the 6th power. And so with that in mind, it now becomes obvious that cosine of x is the inside function, raising to the 6th power is the outside function. So to take the derivative, what we do is we take the derivative of the outside. Well, that's something to the 6th power, so that's going to be 6 times cosine of x raised to the 5th power. That's using the rules of, the power rule. Just move the 6 here and subtract 1 from that. But then we have to take the derivative of the inside. Well, the derivative of cosine of x is negative sine of x. And so what we get as a final answer is negative 6 sine of x cosine to the 5th x. And that would be our final answer. Negative 6 sine x cosine to the 5th x. Just once again, rewriting this into a little bit more, this is the user-friendly form, but a more acceptable form is to put the 5 right there. So that's the answer to number 3. 4 and 5 are going to fall into pretty much the category, except it doesn't tell us to split them up. And any time it says split them up, that's just extra stuff. Remember, take the derivative of the outside times the derivative of the inside. And when you take the derivative of the outside, the inside doesn't change. That's a very, very important part to this. So number 4, y equals x cubed cosine x minus 6x sine x minus 6 cosine x. Well, I'm not seeing things within, functions within side functions. I'm just seeing a whole bunch of product rules that I'm going to have to use. So y prime will equal, okay, take the derivative of this, 3x squared, leave the second one alone, plus take the derivative of this, so that would be a negative sine x, and leave the x cubed alone, minus, okay, now I have this. This is a product rule also because I have something of x times something of x. So that says take the derivative of the first, 6, leave the second one alone, plus, as long as it's inside brackets, I can do this, leave the first one alone and take the derivative of the second, which is cosine of x, minus, now here this is just a simple derivative because it's just one expression of x. So the derivative of 6 cosine x is a negative 6 sine of x. So let's see what all I can simplify here. This will equal 3x squared cosine x minus x cubed sine of x minus 6 sine of x minus 6x cosine of x plus 6 sine of x. And I look, will there anything simplify? Well, the negative 6 sine x and the positive 6 sine x cancel each other out, which leaves 3x squared cosine of x minus x cubed sine of x minus 6x cosine of x. Now realize number 4 in this particular problem had nothing to do with this section. It was entirely last section, which should be a warning. Just because it's in this section does not mean you have to use those rules. Number 5. Number 5, we have r equals the secant of theta plus the tangent of theta, all raised to the negative 5th power. Now here we actually do have something going on. We have an expression on the inside, and that whole expression is being taken to the negative 5th power. So this is chain rule, which says the following. Leave the inside exactly alone, or leave it alone, but take the derivative of the outside. So that would mean take this negative 5, bring it out front, this would be negative 5, and then subtract 1 from the exponent, we get negative 6. But then we have to multiply that whole thing by the derivative of the inside part, which is secant theta plus tangent theta. The derivative of secant theta is secant theta tangent theta plus the derivative of tangent theta is secant squared theta. And so it's all this right here times this, and then we just need to write it into a more user-friendly form, I guess is the way to look at it. And so here we go. We end up with negative 5 on the top, secant of theta plus tangent of theta raised to the negative 6th. We can move that all down here, down in the denominator to get that. And then we have the, actually between secant theta, tangent theta plus secant squared, we can actually pull out a secant theta just to make our lives a little bit easier. So I'm going to pull out secant theta, and that's going to leave the tangent of theta plus secant of theta. Now, notice what happens here. We have secant of theta plus tangent of theta raised to the 6th power in the denominator, and we have secant of theta plus tangent of theta in the numerator. So that means one of these will cancel with one of these. And so our final answer becomes negative 5 secant of theta over the secant of theta plus the tangent of theta the quantity raised to the 5th power. And there is the final answer. You do need to make sure that you try and simplify these if at all possible. And by pulling out the common factor of secant theta, that allowed us to get rid of one of those that were in the denominator. So the final answer is as shown right here. Example number 6. See what that sort of problem gives us. Number 6, we are told y equals the cosine of the square root of 4t plus 12. Now here we've got a problem. We've got really a very nice problem here, because cosine is the outside function and the square root of 4t plus 12 is the inside function. So let's keep that in mind when we actually do the problem. The first thing when we try and find the derivative is the following. We take the derivative of the outside. So that would be the derivative of cosine is negative sine. But we leave the inside entirely alone. We don't do anything with the inside function. But then we have to take the derivative of the inside. Now here's where we have a slight problem. Our inside function is the square root of 4t plus 12. Well, in order to find the derivative of that, we need to use the product rule, or not the product rule, but the chain rule again. First thing, write it in a much more user-friendly form. 4t plus 12 raised to the 1/2 power. So to take the derivative of this, we're going to get 1/2, leave the inside alone, subtract 1 from that gives us negative 1/2, but then we have to multiply by the derivative of the inside. Well, the inside is 4t plus 12. Well, not the derivative, the inside is 4t plus 12, so the derivative would be 4. So we have to multiply this whole thing by 4. Now realize that's still in just an attempt to try and figure out what has to be multiplied by here. So 4 times 1/2 times this will equal 2 over the square root of 4t plus 12. And that's just taking the 4 times the 1/2, which is 2, and then the 4t plus 12 raised to the negative 1/2 power puts it down in the denominator and the square root. Now the question is, can we simplify any of this? Will this square root of 4t plus 12 simplify with this square root of 4t plus 12? Absolutely not, because this is the sine of this, and this is just, in essence, the coefficient that goes along with it. So our final answer is going to be negative 2 over the square root of 4t plus 12 times the sine of the square root of 4t plus 12. And once again, these two cannot simplify, because then what would you be left with? You can't simplify an argument for a trigonometric function with something that is not an argument for a trigonometric function. And so this is the final answer as shown. Number 7, we are asked to find y double prime. Well, this may entail quite a bit of steps to get to our final answer. But what we get is y equals the square root of x minus 5, all raised to the negative 5th power. Now it's already in user-friendly form for the most part. But realize we've got an expression and we're raising it to the negative 5th. So to find the first derivative, what we're going to do is the outside function is raising to the negative 5th. The inside is this stuff here. So the outside would say, okay, the derivative of the outside, bring the negative 5 out front, leave the inside exactly alone, subtract 1 from that, but now we have to take the derivative of the inside. Well, in order to take the derivative of the inside, we need to have a user-friendly form. Well, this is x raised to the 1/2 minus 5. Now, taking the derivative of this, we would bring the 1/2 out front, subtract 1 from it, and the derivative of negative 5 becomes 0. So this whole mess here will become 1 over 2 root x, as shown like that, because the negative takes it down below to the 1/2 power, takes the square root of x. Now we just need to straighten this all up and see what we end up with. So I see that the -5 is going to have to go up on top. This square root of x minus 5 is going to go on the bottom, so that we get a raised to the 6th power. We need the 2 that still stays there, so that 2 is going to go right there, and then we multiply by the square root of x. The square root of x could easily fit over here as well, except I'm out of room. And so realize all I have done is just cleaned this up, and there is the final answer. -5 over this whole mess, 2 times the quantity root x minus 5 quantities to the 6th power times the square root of x. Oh, wait a minute, we haven't finished it, because now what we need to do is we need to find the second derivative. So really why I did this, I don't know, because what I want to do is really keep this in a user-friendly form, which I never did really have it in a user-friendly form, so let's rewrite it into a user-friendly form. -5 square root of x minus 5 raised to the -6th power, and then this would be times 1/2. I can take care of the 1/2 pretty easily. X to the -1/2 power. Okay, so we've got quite a mess going on right here. Let's see what we need to do. We have a product. We have this product here times, or this expression times this expression. So we're going to have to leave this alone, take the derivative of this, plus leave this alone, take the derivative of this. But in order to take the derivative of this, we need to use the chain rule. So we do need to be very careful here, because we have an expression of x raised to a power. We have an inner function and an outer function. So we're going to have -5 halves times whatever it amounts to. So I'm just going to put the whole thing inside a whole set of brackets here. So let's leave this one alone. Square root of x minus 5 raised to the -6th power. Take the derivative of this. So that would be times -1/2 x to the -3/2. Plus, now I'm going to leave this one alone, x to the -1/2 times the derivative of this. But in order to do the derivative of this, we need to use the chain rule. The chain rule says, okay, take the derivative of the outside one, which is raising it to the -6th power. So it's going to be -6th power times square root of x minus 5 raised to the -7th power. And then we have to take the derivative of this inside. Well, the derivative of the inside we have already determined to be x raised to the, or 1/2 times x raised to the -1/2 power. That was from the previous derivative. Now we have quite a mess to have to clean up. And so let's see what we've got. We've got -5 halves times everything. Let's see what happens here. This becomes square root of x minus 5, the whole thing raised to the 6th power. That's in the denominator. We need a negative, and we need a 2 down here to take care of this 2, and x to the -3/2 would be x to the 3rd power, take the square root of that, and that's all under 1. So that's what this whole mess equals in a more acceptable form. Dealing with this mess here, that would be plus, okay, let's see what we've got. X to the -1/2 means this goes in the bottom. We get -6 up here on top, because the -7 does not affect that, it only affects this stuff down here. So square root of x minus 5 raised to the 7th power. We need to put another 2 down there, and we need to put another square root down there. So in other words, what happened here is I wrote this down just a little bit too early. that becomes an x when we take the square root of x times the square root of x down there. Now the only thing left is to actually distribute this 5/2 and simplify this a little bit, because the -6 and the 2 will simplify to a 3. And so finally, when I distribute this the -5/2 to everything here, this becomes a positive 5/4 times the square root of x minus 5, all raised to the 6th power, times the square root of x cubed, minus (3 over x times the quantity square root of x minus 5. And even though we could even go raised to the 7th power, we could go and find the common denominator, and from there, at this point, I am looking strictly at this is perfectly fine for this particular problem. Okay, number 8. Second derivatives aren't always very nice when we have to deal with the chain rule, but something that we just really have to contend with. So we have number 8, which is y equals 3x to the 5th times 4x minus 6, the quantity squared. Now here, yes, we could use the chain rule, but we would use the product rule, because we'd have to take this times this, and in order to find the derivative of this, we would have to take the chain rule. But I'm also going to say, you know what, it's not too difficult to take this to the 2nd power. So I'm just going to rewrite this in perhaps a little bit easier form. So it's going to be 3x to the 5th times, now foiling this out, we get 16x squared minus 48x plus 36. And then I'm actually going to distribute this 3x to the 5th, and so I'll get 48x to the 7th minus, what is that, 96, 144x to the 6th plus 108x to the 5th. Now all I have done is just rewritten this. Now this is a whole lot easier to deal with rather than trying to take the chain rule and stuff like that. Do not forget that if you can, go ahead and change things so that it becomes easier to begin with. And so, taking the derivative, finally, the first derivative of this is 48 times 7, which is 336. So 336 x to the 6th minus 144 times 6 is 864 x to the 5th plus, and 108 is 540 x to the 4th. That's the first derivative. Second derivative is just do the same process again. And this becomes 2016 x to the 5th minus 864 times 5 is 4,320 x to the 4th, and 540 times 4 is 2,160. Oops, 2,160 x cubed. And so I spent a little bit of time at the beginning trying to make it a little bit easier to take the derivatives. So the same rule applies. If you can get it to be a little bit simpler, do so. It's going to make your life a whole lot easier. Now number 9 actually puts it in terms of composition, but it's no different than what we have been doing in the past. And we are asked for a very specific value. So once we find the derivative, we'll be ready to go. Okay, so here we go. Number 9 is f of u is equal to u cubed, but u is x plus 4 over x minus 2. So we need to cube that. And so the question becomes, we are asked what is the derivative of this, because I'm just taking f composed with g. G is the inside function. F, we are told we need to cube it. And so the inside function, the outside function. So to take the derivative of this, if this is equal to y, I'm going to say y even though it's technically f of u, but that's okay. Y prime will be, take the derivative of the outside. So that means 3 times, leave the inside alone. And of course that exponent has to change a little bit. But now we have to take the derivative of the inside. Well, in order to find the derivative of the inside, we need to use the quotient rule. So that will be ho d high minus high d ho all over ho ho. Now it's just a matter of cleaning all of this up. So let's see what we'll get. In the denominator, x minus 2 is squared also, so x minus 2 squared times x minus 2 squared will be x minus 2, the quantity, raised to the 4th power. We will have a 3 on the top. We will have x plus 4 squared, and we will have this simplified out, which will be, let's do the simplification up here, x minus 2 minus x minus 4, because I need to distribute this negative. And notice the x's cancel each other out, so that just leaves a negative 6. So we have this whole mess here, and it doesn't take much to simplify this a little bit further. 3 times negative 6 is negative 18. Negative 18 times the quantity x plus 4, the quantity squared, all over quantity x minus 2 raised to the 4th power. Number 10. Number 10 is very similar. Let's see. We need to find the tangent of pi times u, but u is x squared. I'm just simplifying in all over 2. You know what I forgot to do at number 9? I forgot to actually plug in the value of 3. So let's postpone this temporarily and go back and finish number 9. Number 9, or here's what y prime is, so now we need to actually plug in the value of 3. So plugging this in at 3, we get negative 18 times 7 squared over 1 raised to the 4th power. That's negative 18 times 49 all over 1. And negative 18 times 49 is equal to negative 882. And so that, to complete the problem for number 9, we get that. I just forgot to plug in that final value. Okay, so number 10, getting back to number 10, we have the tangent of pi, and I replaced u with x squared over 2, and we need to find the derivative. Well, we have the tangent is the outside function, the inside function is pi x squared over 2. I know this is a function because it's got a variable rather than just numbers. If it had just numbers, then we wouldn't really have to worry about it. And it's not just a plain old x either. If it were a plain old x, this wouldn't be too much of a problem either. So what we're going to do is we have to take the derivative of the outside function, which is tangent. The tangent, the derivative of that is secant squared. So if this is y equals, then y prime will equal the secant squared, leave the inside alone, times the derivative of the inside. Well, the derivative of the inside, we have to take this exponent 2 and bring it out front, so that's going to be 2 times pi over 2 times, and subtract 1 from the exponent, and we get 2. Notice that the 2's will cancel each other out. So what we're left with is pi x times secant squared of pi x squared over 2. Once again, we can't multiply this times the argument here because this argument goes with the secant squared. This just serves as a coefficient. And so now we need to actually plug in the value of, what is it, 10? And so we get 10 pi times the secant squared of, okay, 10. If I plug in 10 here, 10 squared is 100. 100 over 2 becomes 50 pi. And so I need to do some thinking here. Okay, it's going to be 10 pi. Okay, secant of 50 pi. Well, 50 pi is equivalent to 0. And if I think of secant of 0, the secant of 0 is 1 because the cosine of 0 is 1 and the reciprocal of 1 is 1. And then, so I've got the secant of 50 pi is 1, so the secant squared would be 1, and so I get 10 pi times 1, or 10 pi, as our final answer. Number 11. Number 11 and 12 are asking us to just pull values out of tables and to determine what are some of the results that we get. And so we are asked to find what is find the derivative with respect to x of the given combination. So we have 1 over f squared of x. Well, once again, the process is write it into a user-friendly form, which means this is f to the negative 2 of x. Now realize negative 2 is the outside function, f of x is the inside function. So with that in mind, to find the derivative, if this is equal to y, the derivative will equal, take the negative 2, bring it out front, and subtract 1 from that. So negative 2 times f to the negative 3 of x. But then we have to take the derivative of the inside function, which was the derivative of f of x. And we are asked specifically when this occurs at 4. So I just need to start plugging it in. Let's rewrite this first into a more acceptable form because it's actually easier to do the calculation once we do that. So this becomes negative 2 over f cubed of x times the derivative of x. We have to be careful of derivative versus that looks like a 1. Okay? And so this will become negative 2 times the derivative of f at 4. The derivative of f at 4 is 2. I just got that from the table. And then I need f cubed of x. Well, x is still 4, so f of x is negative 3, so I need to know what is negative 3 cubed. And then, now that we've got this, it's pretty simple to do the calculation. Negative 4 over negative 27, which equals 4 27ths. Final answer is 4 27ths. Realize that it's not just negative 2 f of negative f raised to the negative 3 of x and then solve. You have to remember to take the derivative of that as well. Number 12. Let's see how that goes. Number 12. It's 1 over g squared of x. Well, first thing we have to do is rewrite this into a user-friendly form, which is g to the negative 2 of x. Now we can take the derivative. If this is y, our derivative will be, bring the negative 2 out front, leave the inside alone, and subtract 1 from the exponent. But then we have to make sure that we take the derivative of the inside, which was g of x. Now rewriting this into a more acceptable form, negative 2 g prime of x over g cubed of x. And we want to know what is the value when x is equal to 4. So it's negative 2 g prime of 4. G prime of 4, according to the table, is negative 6. Now I need to know what is g of x. at 4. So g of 4 is 3, and I need to take that to the third power. So negative 2 times negative 6 is 12, 3 cubed is 27, and the final answer would be 12 27ths. Number 13. We're getting there. I apologize for the length of this video, but the chain rule takes a little bit of getting used to. Okay, so we have the velocity is equal to ks squared, and k just represents a constant, so we're going to treat k as if it's a number. Now, at the instant that the body has fallen s meters from its starting point. Now find the body's acceleration as a function of s. Well, acceleration is simply the derivative of velocity. So this is pretty simple. K is just like a number. And so this could be a 2s squared or a 18s squared or whatever. That's all that matters. And so this is a simple derivative. There's no chain rule required. All we have to do is take the 2 times whatever was there and subtract 1 from the exponent. And so it'll be 2ks. And this is still as a function of s. It still has s as its variable, because we have to remember k is just a number. It's just we don't know what that number is. And then finally, number 14. And hopefully I've got enough room here. Number 14. The position is given with this. S equals a sine of the square root of k over mt. The value a is an amplitude, k represents the measure of stiffness, and m is the mass, and we need to find the object's acceleration at time t. Well, that simply means this becomes what's the derivative of s with respect to t? That's all we're asking. ds with respect to t. Well, this one does require the chain rule, because what we have is we have the sine of an expression of t. Now, if this were just t, it would be pretty simple. It would be a cosine t, and we'd be done. Fairly simple. But what we have to do is we're going to treat this just like it's a variable, or a constant, a number. We're going to treat this whole thing, the square root of k over m, as a number, and all we need to do is find the derivative. So that's going to be a times the derivative of the outside. The outside is sine, so the derivative will be cosine. Leave absolutely everything alone on the inside. But then we have to multiply by the derivative of the inside. Well, the derivative of the inside, thankfully, is fairly nice. It's just, what's the derivative of the square root of k over mt with respect to t? Well, the t has a 1. We put the 1 out here and subtract that, so the t disappears. So it just becomes the square root of k over m. And so, to clean all this up, we get a times the square root of k over m times the cosine of the square root of k over m t. And there is the final answer. Oh, wait a minute. Whoops, whoops, whoops. That would be the velocity. Just about messed up completely there. That would be the velocity. But we are asked what's the acceleration. So that means we need to take the second derivative. So we've got this mess. This is number, this is number. So this doesn't really affect anything, but we still have an outside function cosine, inside function there. So, once again, the numbers out here aren't going to be affected. The derivative of cosine is negative sine. Leave the inside alone. But now, we have to take the derivative of the inside, which is the square root of k over m. Now let's see how that all affects everything. And I'm just coming back here to for completion, that we're actually taking the second derivative here. Square root of k over m times square root of k over m becomes k over m. We have to throw in the negative that was there, and then it's the sine of the square root of k over m t. And so finally, as a final answer, we get negative a k over m times the sine of the square root of k over m t.